In the name of Almighty God, I am Master Sankoshi, and today I want to talk about particle tracing module. Dispersed flow is a chapter that I want to describe it tonight. In a dispersed fluid, the density of particle is greater than in the dilute fluid described in the previous section, but their volume fraction is still lower than in a dense fluid. The dispersed fluid is the upper limit of the applicability of a Lagrangian particle tracking approach in addition to the bidirectional fluid-particle interaction mentioned in the previous section. Particle-particle interactions may also need to be taken into account. This is sometimes referred to as four-way coupling. Particle-particle interactions can be included in models, but the following limitation apply. The first one is hard sphere collisions are not supported. Forces must vary continuously with respect to the distance between particles, as in, for example, the Coulomb force between charged particles. The next is the computation time scales as the number of particles squared. This is because every particle interacts with very other particles over all distances. It is possible to apply cutoff distance for particle-particle interactions, but the interaction force must still be evaluated for every pair of particles. If the particle-particle interaction law is highly nonlinear, it may be necessary to use a very small time step. This is particularly true if the Lennard-Jones option is selected. The next chapter is particle diffusion. Particle motion in a fluid is a combination of advective and diffusive uh, transport. Advection is the bulk transport of particles by the mean fluid velocity via the drag force. Advection is typically deterministic, given a particle at a specified location in a laminar flow field. The motion of the particle at future times is completely predictable and reproducible, allowing of course some small differences due to the discrete time stepping used by the time-dependent study. If 100 identical particles pass to the same point in a stationary fluid field, each having the same velocity at the point, then all 100 particles will follow the same path. Diffusion, on the other hand, is implemented as a stochastic term that can give different results for each particle in the simulation, even if the initial conditions are the same. There are two main mechanisms for diffusive transport in the particle tracing for fluid-fluid interface: molecular diffusion and turbulent dispersion. Molecular diffusion, the Brownian force. Molecular diffusion is most significant for extremely small particles on the order of 0.1 micrometer or smaller. When such small particles are in fluid of non-zero absolute temperature, the thermal motion of individual atoms or molecules in that fluid causes them to collide randomly with the particles in the directions other than that of the mean flow velocity. These random collisions can cause particles to speed up over time, a phenomenon known as a Brownian motion. The control implementation of the Brownian force involves seeding unique random numbers for each particle at each time step taken by the solver. Therefore, a sufficiently large number of time steps should be taken so that the result show a statistical convergence. In a smaller fashion, the number of model particles should be sufficiently large so that the average behavior of the particles can be clearly seen. So you can see the Brownian motion of particles that are released from a single point. They diffuse outward, upper left, t is equal to 0, and right, t is equal to 10 seconds. Lower circle is lower left, this one, is t is equal to 30 seconds, and the lower right t is equal to 100 seconds. Turbulent dispersion. Turbulence is the dominant mechanism for diffusive transport of microscopic particles in a high Reynolds number flow. Unlike Brownian motion, turbulent dispersion can remain significant even for particles at the micron scales or larger. For laminar flow, the drag force only contributes to the advective transport of the particles. You see that is a force of dispersion or turbulent dispersion is equal to 1 divided by tau p and multiplied by mp u minus v. However, if the fluid is turbulent, then the fluid velocity u at the particle's position consists of a mean flow term and an instantaneous fluid velocity perturbation. This is because most of the turbulence model in Compton multiphysics are variants of Reynolds average Navier-Stokes model. In a Reynolds average Navier-Stokes model, eddies in a turbulent flow are not modeled explicitly. Instead, information about the magnitude and lifetime of eddies is only retained in a statistical sense, often through the use of transport equations for additional dependent variables. Several different expressions for perturbation term exist. The simplest being is U prime is equal to the square root for 2k divided by 3, where tau is a random unit vector and chi is the turbulent kinetic energy. Some turbulence models, such as the chi epsilon model, solve for chi as an additional degree of freedom. It represents the amount of energy associated with eddies in the fluid. Unlike molecular diffusion, turbulent diffusion has a finite resolution in time. The turbulent velocity perturbation experienced by a certain particle is assumed to have the same magnitude and direction for a finite time interval. Based on the lesser of two time scales, the eddy lifetime over which eddies or vortices in the fluid die out and form again, or the eddy crossing time over which particles have sufficient inertia to be thrown out of one eddy and into another one. For extremely small particles, the eddy crossing time may grow so large as to become irrelevant. If the time step taken by solver is made extremely small, eventually the turbulent perturbation term between successive iterations no longer consists of uncorrelated random vectors. The built-in discrete random walk and continuous random walk models compensate for this effect by only seeding the random perturbation term at discrete times based on the turbulent dissipation rate epsilon if it is available. Therefore, it is important to take a sufficiently small time step so that the change in this random number C can be resolved. The next one is refraction effects. Some forces, such as the drag and thermophoretic forces, include high Knudsen number correction that improve accuracy when the particles are extremely small or the surrounding fluid is highly rarefied gas. The refraction effects begin to become significant when the Knudsen number, defined as the ratio of the mean free path of surrounding molecules to the particle diameter, is greater than zero point 0.1. Wall effects. The drag force and lift force include correction terms to account for the presence of nearby walls, improving their accuracy for channel flow, for turbulent wall-bounded flows, and anisotropic turbulent dispersion model is available, taking different fluctuations in the stream wise, span wise, and wall normal directions. Other built-in forces, in addition to drag force and Brownian force, the particle tracing for fluid flow interface includes a wide variety of other built-in forces that can be used to create high-fidelity multiphysics models, including the following. The first one is electric and magnetic forces can be exerted on charged particles. The next one is the virtual mass and pressure gradient forces can affect particle motion in a liquid based on the spatial and time derivatives of the liquid velocity. The next one is dielectrophoretic and magnetophoretic forces can affect particles in non-uniform electric and magnetic fields. The aquastophoretic radiation force affects particle in pressure waves. The thermophoretic force causes particles to migrate in a temperature gradient. This force is most significant in rarefied gases. Lift forces are exerted on particles in a shear flow. You see that this is a dielectrophoretic separation of red blood cells and platelets, the blue one, in a fluid channel. The fluid velocity is shown in gray scale. The electric field is indicated by the yellow string lines. Computing particle mass and temperature, you can solve additional equations for the particle mass and temperature along each particle trajectory when solving for temperature. Built-in features for radiative and convective heating and cooling become available. You can also add user-defined heat sources and sinks if the particles are heated or cooled due to radiative or convective heat exchange with their surrounding. Then optionally, you can compute the dissipated particle heat as a volumetric source or sink term. For example, if hot particles are cooled by being submerged in cold water, you can add the dissipated particle heat node to compute the corresponding heat source term in the fluid, potentially enabling two-way cube simulation of particle tracing in a non-isothermal fluid. When solving for particle mass, you can make particles grow or shrink as they propagate. When releasing particles, you can enter the initial particle mass directly or sample it from a distribution such as a long normal distribution with a specified southern mean diameter. As an alternative to specifying particle growth rate directly, if the particles represent liquid droplets, you can use a dedicated feature to compute the evaporation rate for droplets of a given size and temperature. When solving for both particle mass and temperature, the built-in Stefan Fox evaporation model can optionally include an evaporate cooling term. Thank you so much for watching my tutorial video until the end. Today is 24th of February 2026 and the time is 4:29 in the morning.